Okay, hello guys. First of all, thanks to Mr. Tom King for his work over the last 2 weeks introducing you to networks. And this little video is a summary of what he would have told you. So we introduced first of all to vertices. That's a vertex, that's a vertex, that's a vertex, that's a vertex. Could be representing cities or suburbs, houses. Looks a bit like Belconnen, Civic, Roden and Tuggeranong. So sorry Gungahlin, you missed out. What are we adding now? We're adding edges. Now before we go any further, you should know what the degree of each vertex is. This one's got a degree 2, this one's got a degree 3, 3 and 2. Now in 6a you learned about traceability, and you should have learned by now that a network is traceable if either all the vertices are even numbers. Well, this one is odd, this is odd, so that doesn't work. These two are even, not good enough. Or if two and only two of the vertices are odd. Well, these two are odd and the other two are even, so that should be traceable. Not only that, we know that we can trace this network by starting at one of the odd nodes, doesn't matter which one. Run your pencil along all the other nodes. You should finish up at the other vertex. Let's try that again. Starting at this one, 1, 2, 3, 4, 5, all done. Now, why is that a simple graph? What's the definition of a simple graph? You should know that it is a graph which has no multiple edges and no loops. That's a multiple edge, so this is no longer simple. That's a loop. Another reason why the graph is no longer simple. Now, is it a connected graph? What's the definition of a connected graph? Check it out. You will find that a connected graph is one where you can get from any vertex to any other vertex. So yes, it's connected. But if we add another vertex, this is no longer connected because that graph is isolated. Let's add a few more of those. Well, I've done some of them. That blue graph is a subgraph of the main red one. In fact, in two different places. There, it's a subgraph of those three vertices connected like that. It's also a subgraph of these. It's a subgraph of the red network twice, there and there. What is the definition of a complete graph? Check out the definition of a complete graph. It's where every vertex is connected to every other vertex. Well, that is the case with this blue one, but not with the red one. Let's see if we can make those two graphs isomorphic. Well, we've got 4 vertices, same number of lines. Does that make them isomorphic? Check it out. You've got to check the number of vertices and edges. Now here we have a vertex with 1, 2, 3, 4, 5 lines. This one's got 1, 2, 3, 4, 5, 6 edges. So there must be something wrong with the way that I've done it. These two graphs are not isomorphic. But let's leave them like that anyway. What have we done now? We built a bridge. We once again have a connected graph. Next thing I want to talk about is adjacency matrices. If we're going to do an adjacency matrix for the red graph, we need to first of all label all the vertices A, B, C and D, and then do a matrix that we can fill in like that. You put a number for the number of connections between any two vertices, so A to A has none, A to B has 2, A to C has 1, A to D has 1, and so on. B to B is the only time when the numbers in the leading diagonal are not 0. That's the leading diagonal down here. And that's what your answer should look like. Check it out. Make sure there's no mistakes. Do we have a planar graph on the screen? Remember, the definition of a planar graph is when none of the edges crosses another edge. So we could not draw a line from there to there because these two lines will be crossing here. We'd have to go around the outside if we wanted to keep it planar. Alright, so let's move on to Euler's formula now. Now we'll just look at the blue graph, so we'll have to get rid of some of the green graph line there. Draw a box around the shape that we're interested in, as there is always a limit to the area in which a network sits. Vertices, faces are in between, let's colour them in, and one for the outside. Vertices 1, 2, 3, 4, edges 1, 2, 3, 4, 5, 6, 7, faces 1, 2, 3, 4, 5. Check out that V minus E plus F equals 2. Okay, let's look at walks, trails, paths, circuits and cycles. First of all, we need to repair the walk, like that. Okay, a walk can go anywhere you like. You can go up here, you can go down there, you can go back up here if you wish, you can go down to there. No restriction on where you go with a walk. A trail is a walk you can take, but you can't repeat any edges, so once you've gone down there you can't go back. That is a trail. You're okay as long as you don't cover an edge twice. That's as far as you can go with this trail. Path is a walk with no repeated edges and no repeated vertices. Let's go down here. Can't go on that loop because that would be a repeated vertex, but we can go down here, we can go down here, we can go across to here. And that is our path. A circuit is a walk with no repeated edges and you finish up where you start. So we can go around there. We're allowed to go around there because we're allowed to go through the same vertex twice. And we can go back down there. That is a perfectly good circuit. A cycle is a walk that's got no repeated edges, no repeated vertices,